today. It is on modeling, and there's an abstract in the agenda. If you haven't read it, I encourage you to read it. It's going to touch on a bunch of the topics we're going to talk about today. We are going to, much like the other previous panel before here, kind of take questions. We have topics and kind of a plan to kind of cover a couple different areas in the topic of modeling during this panel. But we're also, if there are questions from the audience, raise your hand. Come see Jeremy. He has the microphone. So feel free to speak up because we do want to engage. We don't want to kind of talk for an hour and 15 minutes and then take all questions at the end when there's probably they're more applicable to take the questions where they're relevant to what we're conversating on. So with that, let me introduce the panelists here. So to my immediate right, I have, so I'm going to introduce them and then they're going to give kind of a little bit, take a couple minutes to give some background and perspective, kind of where they work within the field of modeling. So just kind of give it. So to my right here is Ted Kaplan of RFK Engineering.
Okay, yep. I'm Ted Kaplan. I'm the CEO, co-founder, and system engineering of RKF Engineering. We were founded in 2001. We do wireless communication system and regulatory engineering. We have a large part of our work is in assessment of interference paths and characterizing sharing. And we have a large, robust database of both standard models and homegrown models that we use. In terms of relevant work, I'd say that in the last 5 years, I was part of the SSTD AWS3 group that modeled assessments between DoDs coming into the 1.7 gigahertz band and commercial assets there. And I also, and for that, I was an SME for modeling and sim, and we developed several programs, one of which was an innovative ray tracer that maybe I'll talk about. And additionally, we were representing the Wireless Coalition for the 6 gigahertz band more recently, and that opened up the band to our lands. And we were also the company that wrote the Open AFC, or Automated Frequency Coordination Tool, to facilitate standard power Wi-Fi devices in the band and allow and coordinate them with the incumbents. In general, my background has been, in terms of propagation modeling, has been more on the side of using models and interpreting models rather than building them from scratch. But that's my background.
Thank you, Ted. Next, Ted, and I don't know if you guys planned this, but you sat in the order that you list, so excellent, is Roy Sun of Cable Labs.
Yeah. Thank you, Billy. This is Roy Sun, principal architect from Cable Labs. Cable Labs is an innovation and research center behind many operators globally. So before joining Cable Labs, I was a developer of channel models. But after joining Cable Labs, it's more likely using channel models from the industry or from the operator's perspective. At Cable Labs, I joined Cable Labs 6 years ago, mainly working on spectrum sharing problem. But sometimes we also have some activities to develop the channel models on our own. So for spectrum sharing, we did a lot of work in the CBRS band and other 3 gigahertz band. So there are a lot of familiar faces in the room. We also work on 6 gigahertz spectrum sharing a few years ago and made a lot of contributions to the FCC and also a lot of contributions to either 3GPP or IEEE.11 working groups or ETSI brand. And currently, we are working on the 7 and 8 gigahertz spectrum, as well as the 3.1 to 3.45 gigahertz spectrum sharing issues. Besides this, I also go to 3GPP Run 4 working group from 5 years ago. At 3GPP, I'm mainly focused on the spectrum sharing issues. So there are a lot of spectrum-related issues in 3GPP. Before joining Cable Labs, I worked at NIST in the same building with Billy from 2015 to 2018, designing millimeter wave channel model, channel sounders, and also doing some channel measurement campaigns over there. And before that, I was a PhD student at the University of South Carolina and doing channel modeling with NASA on the air-to-ground channel models at a 1 gigahertz and 5 gigahertz band. Yeah, that's all.
Excellent. Thanks, Roy. And then last but not least, we have Tinjun Chen of Duke University. Yep.
Yep. Hi, everyone. My name is Tinjun Chen. I'm assistant professor of electrical and computer engineering and also computer science at Duke. My background is actually in general fields of wireless and optical networking and communication systems. In terms of the spectrum sharing and modeling, I've been working on basically doing measurements. One of the first 28 gigahertz measurements in Manhattan when I was a grad student at Columbia, where we actually look at how signals propagate in very dense urban canyon environments in cities like Manhattan. And then later on, I moved to Duke, and then I've been working on spectrum sharing solutions, both on the hardware side and also on the software side in terms of spectrum sharing, particularly in the CBRS band. And then now we're looking also at the the 6 gigahertz band and also the recently emerging 3.1 to 3.45 gigahertz band. So on the hardware side, we built systems which are very wideband, ADC-based systems to capture large spectrums of bandwidth, and then we try to do a lot of signal processing in hardware to basically meet all the latency and processing deadline requirements. And on the software side, we've been looking at mostly putting together scalable and efficient frameworks, building on open source databases of buildings, terrain profiles and other type of public information, and also using the NVIDIA's Shauna ray tracing tool to basically put together these open source tools to build a scalable pipeline that allows you to actually crowdsource environment information across a lot of different areas, and then basically do ray tracing and then train machine learning based models and statistical based models to perform RF propagation modeling. So if you look at our recent work, for example, from DICE-Band 2024, we were able to run this pipeline very effectively to crowdsource, let's say, the entire U.S. territory in terms of basically including building information into the ray tracers scene, and then performing ray tracing across very different environments. And then we built synthetic models that captures the propagation behaviors in very different environments. And then on our Duke campus, we also recently have been working with a third-party vendor who has been deployed private LTE networks operating over the CBRS band, where the SAS is actually provided by Google. So we are kind of in a unique situation where we're about 2 miles away from the East Coast. So we are now trying to understand how SAS actually controls the licensing of CBRS band, where we're only 2 miles away from the 2 hours of drive away from the coast. And then we've been actually running a lot of measurements using commercial phones to collect CBRS coverage on our campus. And then we try to use these measurements to correct for and also to validate our ray tracing based coverage models. And then those results seem to be quite promising as we have seen so far. I guess I'll stop here now.
No, thank you, Tinjun. So I'm gonna jump in. I was originally going to start somewhere else, but based on the conversation that we've kind of had this morning and coming in here, I'm going to skip a little bit and kind of jump into a little bit more in the sense of this idea of how do we formulate. So you've heard even here just across three panelists different methods of kind of how to construct models. Tinjun just talked about kind of ray tracing. We hear about different types of channel models and more kind of physics-based propagation models. We talked about this a little bit earlier today. I said some words on things like that. And let me start, Ted, specifically, I'll start with you here first, is, when we talk about modeling, you have sets of requirements, and we talked about earlier, there's conversation about how you want to design the models for the problem you're trying to solve. How do we go about making those decisions of the type of models? Whether we're looking for statistical-based models, site specifics, empirical, based models? How do talk to that? Because that's really the first real decision as we start to kind of go down this path in model development that we have to make.
So I think that in general, you have to be immersed in the problem. So Working Party 3, I am inviting you to come to Working Party D and 4A and whatever else.
I don't want to.
I think that's sort of a requirement because as we saw from Chris in the last panel, there's a lot of things that go into these models, a lot of considerations, not just frequency, elevation, angle, distance, but also things like are you using advanced antenna systems? You need to model, as we've been talking about, delay, spread, angle, arrivals, and things like that. Are you modeling a very large deployment of things? When we did the analysis for 6 gigahertz to show that that would be shareable, we did a US deployment of Wi-Fi devices. The analysis was on, I think, 6 AWS servers. It ran a month. So we were really, we didn't have GPUs or anything, but still, it took a long time. So, and so we weren't doing ray tracing for that, for example. But, and so the other thing I would say is that one thing that something like a Working Party 3 doesn't, I don't think, consider is because you may not need a certain level of accuracy, there may be simplifications in the model that help you speed it up if you have to do a physics-based model. So empirical models as a whole, are based on measurements, and it's hard for users, honestly, to interpret them because of, I could talk about this for a long time, but it's hard to interpret them because we've all talked about this rural, suburban, urban, how do you interpret that? And also things like what elevation angle and what building heights were measured. And we didn't store the measurements. So I think this will come up in another topic, but so I'll skip it. But, I think part of this is keeping track of the measurements that were used to create the models. And I'm getting a little bit off topic. So in terms of setting the requirements, you need to understand what the problem is trying to solve. And initially, usually when you're developing rules, it's got to be based usually on wide area deployments, large scale modeling. In general, less site-specific modeling. So you need some kind of empirical model, or it comes down to that. And then you, at some point, when you're developing real rules and you're deploying systems, you want to have some level of physics-based model out there. And honestly, in the long run, you combine those things with machine learning. I know that, but you need large databases for that. One thing I will say, and I'll cut this short because I may be rambling at this point, is that we've heard a lot of people talk about all the data they have, all the measurements they're taking. It's wonderful stuff. But my experience is that over time, when we create a new model, we have a subset of measurements that model is based on, whereas we don't try to capture, as you're trying to do, measurements in the repository that are available to researchers. So I understand this is not an easy thing to do because you got a lot of metadata with measurements, and you got getting the format, so it's an interchange format so that people can use it is difficult. But if you could do that and extend it, then it wouldn't just be Working Party 4E developing some of these models, but and I know universities are doing it, but I'd be able to do some of this work. So I'll stop there because I think I'm rambling.
No, that's good. And I actually want to go to Tien-Tsin for a second to follow up on that. So you were making the case there for part of it of the benefit kind of statistical based modeling due to the scalability and tractability of some of those problems that we see, especially when we're talking about aggregates and kinds of large scale simulations. Tien-Tsin, I know you, in some of your research with your students, have been looking at machine learning. I've recently been thinking quite a bit about that, and I mentioned earlier today in something I said, it seems to me we have these, in classical modeling, we kind of two general categories, site-specific or statistical, and it's not really, there's a spectrum in between there to some extent. But it seems to me that this application of machine learning to propagation model doesn't really even fit necessarily into one of those two. It may actually be kind of a third approach to talk to that. And you've done some work, and I'm curious in your thoughts of how machine learning can leverage. Is it a completely different way to kind of approach and generate predictions, or is it really something that augment kind of existing methods?
Right. I think that's a very good question. That's also the question that we're trying to answer these days. So my background actually starts from taking measurements, every meter down the avenue in Manhattan, and then building, statistical models from, let's say, thousands of measurement points along. Let's say we did it actually along Broadway over like a few kilometers of distances, and eventually we get, the path loss coefficient, right? That's basically what we get out of these, thousands of measurements, and you get some, shadowing coefficient, but that's all you can get from that equation, right? And later on, I've been looking into machine learning approach for a few years. So typically there's been three main categories, right? So there has been people working on building, both the training set and also the testing set from simulations. Let's say you take a ray tracer, you build your model purely from the ray tracer. There's no measurements involved. And then you train your model based on, let's say, 80% of your ray tracer data, and then you test the model based on the rest 20% of your ray tracing data, right? In that case, you're very likely to get an accuracy that is within, let's say, 0.1 dB of RMSE, because there's no real-world measurements being involved in the validation phase of the model. Everything's coming from the same ray tracer, right? And then on the other extreme of the spectrum, there has been work that focused on purely building machine learning models from measurements, which actually involves a lot of measurement. They have to take thousands of measurements per area. And then what they can do is to say, I take 80% of the measurements in this area to build a model which is very specific for this particular site. And then I take the rest 20% of the measurements from the same area to validate the model performance. And in those cases, people can typically get an RMSE of around 9 to 10 dB. Right? That's kind of a reasonable range of RMSE in terms of modeling that we can achieve today using pure measurement-based machine learning model. As you can see, on the simulation side, you can generate ray tracer data very quickly, depending on the scale, depending on whether it's licensed software versus unlicensed software, whether there's a GPU acceleration or not. On the measurement side, you really have to spend money to get the equipment. It can be very top benchtop equipment. Could be measurements based on cell phones and laptops, and then you build your model based on a large measurement database. So what we are doing is kind of sitting in between. We're trying to find the sweet spot in between where you can leverage the ray tracer as much as you can, and then you incorporate a tiny fraction of measurement data to validate the ray tracer model, and then also to correct for any site-specific errors that the ray tracer may introduce, right? For example, the approach that we've been taking was to say we crowdsource the entire US territory. We pick the lands, we pick the sites where with, let's say, a building to land ratio of greater than 20%. We run ray tracer through all these sites. Basically we can do, I think we look at, if you look at the west half of the US, we were able to find, for example, about 30,000 sites, right? Each is a 512 meter by 512 meter patch. We have about 30,000 such areas that we can use to basically run our ray tracing simulations over. And for each of those areas, we can also crowdsource public information from geographical databases. This can be building profiles, the shape of the building, the height of the building, the distribution of the building, and then we can actually run ray tracing for each of those sites purely in simulation. And then based on those results, we built a machine learning model that is purely trained on synthetic data sets obtained through the ray tracing simulation. And then for an unseen site that people have never seen before, we actually go there and then we take very few measurements. This can be, let's say, 20 measurement point within 500 meter by 500 meter area. And then actually we use those measurements to correct for the machine learning model. And the reason that this works is because when we design the model, we actually incorporate an additional channel, which is basically a sparse signal strength map that you can incorporate into the machine learning model. So during the training phase, that channel is basically whatever data you can get from your ray tracing simulation. And when you actually run inference, or when you actually apply the model, you can replace that input channel with field measurement data. But this is only a very sparse signal map. This can be 10 points or 20 points. And then we show through this combination, you can actually build a machine learning model that is trained purely based on synthetic data. But during the inference phase, when you want to apply the model to a new site that you haven't seen before, you take very few measurements from the new sites. You put those measurements into your pre-trained model, and then the model is going to actually give you a much better inference result, right? So it's kind of a combination of synthetic data-based model together with very few sparse measurement points that's taken from the field. And then there's definitely a site-specific design here. But from our experiences, this actually is able to achieve about 3.5 dB improvement in the RSME. So standard models is being able to get about 9 to 10 dB RMSE. And then if you actually do our approach, you actually reduce the RMSE from 10 dB to about 6.5 dB. Right. So that's kind of the approach that we've been taking.
That's exciting stuff to me. We have sort of a related effort that we started, much smaller scale, but we built for SSTD a ray tracer that was tunable in a lot of parameters, including buildings, electrical properties, and scattering, and uncertainties, path loss factors, and angles of arrival, things like that. And also phase, because you can never measure phase of a ray exactly. It's only centimeters before you're 60 off, right, in these frequencies. So we took ITS measurements from 6 cities, and I don't know if they're accurate, but you can tell me.
They're perfect. What are you talking about? Gold standard.
But we didn't have enough to do machine learning, we felt. So what we did was optimization. Our goal is to do machine learning if we have big enough data sets, and I'd be interested to get your opinion on how much you think that requires. But what we did was we did optimization. We did it 2 ways. We did for each city, we split the data in half, and we optimized based on half the data, and we predicted the other. And then the other way was we took all the data from all the cities, the test data, half of them, and we came up with optimum for all 6 cities, and then we applied that across the ray tracer across all the data set that wasn't part of the test set. And what we found was what you said in general was the MSE was about 9, 10 dB. But what was interesting was that the shape of the curve was very good. It was just the tail, which is the important part, of course. And I think that you can, one of the things you can do in the tail, I guess with more data, it would help. Also, I just need to say that one of the restrictions is in our model right now, we don't have building face information. We don't have electrical properties of each individual building. So we're coming up with an average for that area of what the building characteristics are, which is, I think a limitation of this stuff. So that was a long discussion, but what I really wanted to get to was what my focus was on speeding up the ray tracer. What could you eliminate from the ray tracer in order to get it very fast? And what we found was that a lot of the propagation, the calculation time was a diffraction. So we restricted ourselves to just calculating the diffraction along the main path, and not along reflected paths. And we found that it didn't, in terms of tuning the parameters, you got similar results. The other thing which we didn't get a chance to do, and I think we need a larger data set to do, is restrict yourself to dominant paths. The optimization or the machine learning specifically should be able to compensate for the secondary effects in the propagation, and you shouldn't need to show 2nd and 3rd order reflections to get that. So I would love to continue this work, and it's really interesting.
So
so go if you want to say something quick, because I want to ask Roy a question. Kind of, you guys are talking about something, and you're talking about model development, and you're throwing out numbers of RMSE and kind of how you're validating. But I think I want to spend a little bit of time on that as well. Specifically, how do we validate models? So you're hearing here different approaches, both they've done in the past and they're looking at now. And I'll ask Roy first, but then you guys, I'd be interested in your take. Is how do we actually go about RMSE is your traditional metric, but it's not necessarily the only way to validate that. And especially when you start to think about ray tracing, machine learning, some of these other approaches too. How do we really validate these models to build trust in how they're performing? And so I'll ask Roy first, if you want to come out this, when you guys at Cable Lab and you're working on these things, how do you, if you're proposing a model, go through it? Is it besides just the traditional RMSE? How do you look at how the performance of a model is? Or I should say, let me just, sorry to interrupt, but or compare two models, right? When you're cross-comparing what they are.
Yeah, we sometimes compare model, or in other words, we validate models. For example, a few years ago, Mark and I used the Winner2 model to do the 7 gigahertz coexistence study. FCC recommended to use Winner2 model. Winner2 model was initially designed up to 2 gigahertz and then enhanced to up to 6 gigahertz. But we need to apply that model for 7 gigahertz. So we did a measurement campaign in Boulder or Louisville area in Colorado at 7 gigahertz. And then we compare our data with the Winner2 model. We also compare that with the 3GPP model or the NYU close-in model, and find out, oh, the Winner2 model could be extended to that frequency. So that's an example how we evaluate the model or validate the model.
Yeah, I don't know if you guys, either of you, Tingen or Ted, one of the things I think of when we talk about, and it was actually, I can't see where I'm looking anymore. Tony mentioned it during one of his questions, because I had in my notes to bring up, is, he talked about the previous panel, the tails of the distribution when you're thinking about aggregate. And it's one of those things that, there are times when you try to fit or you evaluate a model just within a certain sort of area. So, for example, the generation of the slant path model in 2108, section 3.3, it's an empirical model based on synthetic data, as you talked about. I can talk about, I have comments on that too, but it's based on synthetic kind of ray tracing based data. But a lot of effort went to making sure that it was really valid, because it was designed for a sharing scenario specifically, as within the scope of study group 3. A lot of effort was made sure that it had a very good prediction based on the data at the interference side of the distribution, to some extent at the expense of the rest of the distribution. I don't know if Chris Anderson is still here. He talked about this a little bit. He touched on it. But right, it's not just using all the measurement data, but basically looking at what are of those measurement points and of those scenarios, which are going to dominate the types of problems we're solving. And let's essentially bias our evaluation of a model to those sorts of scenarios. And so it's not just, here's all my data, it's this subset of data I know is going to be the most impactful. So that's really what we want to optimize to. I don't know if you have a comment on any of you on that.
Well, there's a couple of things you said. So first of all, in terms of validating data, I think it's unfortunate that a lot of models are validated by being used often. We've used it here, here, and here, therefore it's valid, right? That's a problem. I think that one way, you need to have sensitivity studies, you need to have measurement studies, and that show the goodness, where it's good, where it's not good. I would give an example of P1411, which has the companion report 2046, I think. I think that's it. And then the document includes, first of all, empirical models, which this is for short distance path loss with clutter. So it includes the short distance with clutter, and the empirical models with the antennas in the clutter and with one antenna above the clutter, and it includes ray tracing approaches and equations for implementing them for the same scenarios. And it has a companion report which shows sensitivity studies against measurements and against, I guess, the other models, the empirical versus the other. What it's missing is there's a lot of models that do similar examples. They also talk about the measurements. They give background on the measurements, but they don't save the measurements. So I would say that I like that one thing it doesn't do is there are a lot of models in force effectively that do similar things like how to model and others, and there's no comparison against that. So it's hard to say when to use which one. They cover the same frequency bands and things like that. I'd say M2135 is similar. I'd say that You could say winner 2. You could say 2108 if you had free space laws for the short distances type thing. So all these models, I think, to validate them, need the measurements, need to be compared, and have real documentation on sensitivity, so that it's just not anecdotal. What was the other question?
No, you touched on a bunch, and that's, I was basically saying, how can we better, fuller validate a model as opposed to just looking at all the data? Is there cases where we kind of sub-select data that we know based on the problem that we're trying to apply the model to say, this is the most, right? So this comes back to like requirements, and we generate the problem. Those requirement lists, or those kind of where the problem is trying to attack, generally there's a priority of importance of what the model's trying to solve. And then there's primary benefits and secondaries. And when you have your measurement data, can you essentially separate or bin your data to kind of target those areas, and then weight your evaluation of a model based on that? Not here's the whole CDF and we kind of RMSE for all data, but there are certain areas where line of sight sort of conditions, these sorts of conditions are going to dominate the analysis that's really going to consume the model that we're generating.
I have an opinion on that too.
Go for it.
Well, first of all, so I think that part of the problem is the speed of the analysis that needs to be done, and whether it's real time or not, and all the other issues with these models, and which one you apply. But on a site-specific basis, I believe that if you're going to deploy systems like that, you may also want to have risk assessments. Risk assessments, you can spend more time for site-specific modeling. You can certainly provide maps of where the line of sight locations are, the high-risk locations. You can provide locations where the I over Ns are likely to be greater than, 5 dB or something, less than 5 dB. Yeah, so again, high risk. So you can map these things as a risk assessment, and it's up to the regulations to take care of that if something happens, and you have to go back to the risk maps and stuff like that.
So I'd turn this question I'm going to ask to Roy here, in the sense of, when we're doing these sorts of analysis, at Cable, as you're working with actual deployments and scenarios, because you're, as you said, you're dealing with operators and kind of deploying scenarios, you work in the CBRS and systems. And so, in your case, I would imagine it's easier to pull in some of those details of, how deployments are go. But I also would ask, a lot of times we look at these kind of, what might, you're looking at 6, 7 gig or 7, 8 gigahertz right now, right? How do you detail some of those risk assessments for systems that aren't actually deployed? There's been talk in the past system where we've rolled out in certain bands where we've talked about the technology, what it's going to be, and then it's changed. Not necessarily, I'm saying that in a negative way, but it's evolved. Even CBRS has evolved from the original picture of how that deployment was going to be. Now we're talking different types of base station access points, right? Hey, we can do more with that. And generally it's a good thing. When you're looking at these new bands kind of trying to lead up in the front, how do you take into consideration, right? Because there's this idea of, there's some uncertainty as to, we think what's going to be deployed initially, but we want to keep this open to, and that models that can kind of forward look on that.
Yeah. So for research, it's always before the real deployment. We don't have really deployed data as a feedback when we initially doing the research. And we need to rely on the channel models or some other simulation studies at the beginning stage. Go back to your original question about what Chris mentioned in the previous panel in a CDF curve about a propagation loss. So as operators, mainly concern about the tails with high loss. But for interference, we concern about the tail with the low loss. But if we go back to the measurement, or to the main topic of this panel, how to define the requirement of the measurement or modeling, majority of the data is in the middle. It's not on the two tails. And we can rely on the mean value or the median value, but can we really rely on the values on the two tails? That will require a significant more data amount of more data to cover the two tails. And that's some additional requirement for the channel modeling or measurement. And that also impacted the question you mentioned about how to evaluate the performance. If the data samples is not large enough, probably we cannot really rely on the tails for, to address our concern.
Essentially what you're talking about is the confidence in your model is almost a function of where you are in the distribution of the losses kind of you're thinking of.
Yeah.
Yeah, no, that's a good point. And I will pause because we've been talking about it. Are there questions? Like I said, you could raise your hand, Jeremy has a microphone, or I will keep going. I see Tony, they're back there, and I saw another hand too. But
you can pick me out of this place. So Billy, I want to maybe just revisit something. You said something in passing, which I thought was extremely important about the RMSE, and I want to focus on the M in the RMSE, the mean. Right? There's a lot of different. You can just take a distribution, you can calculate the mean. We all know how to do that. But I think it's important if you're trying to develop a model for a specific requirement for a specific use case, you have to know how to properly calculate that mean so that it's actually a proxy value for clutter in your parent model. Right? I want to get into this a little bit in our panel tomorrow, but I think it's important that before we just start adopting like a parameter like RMSE, that we actually stop and think about how the mean is calculated and make sure that what the results then that we're getting are really indicative of what's going on there. So I guess that really wasn't a question, but maybe it is a question. Does anybody ever think about that? And if not, why not? Why aren't we taking into account how the model ultimately? Because I hate to say this, but we don't really care about clutter, right? Those aren't the questions we ask. Are we going to get interference? Can we close the link? Nobody actually cares what clutter is, right? So if you don't answer your question, if you don't answer it in the context of why you want to know clutter, if you don't keep that in mind, you can go very far astray very quickly. So the question is, why aren't we doing more of this? Thank you.
Well, I'll say on that point, and I'll see if Transform's fun, that we talk within our group of modeling. We obviously when we propose some iteration on a model, we have RMSE. We of course generate that number, but we have conversation of what is even simple things like the standard deviation and the spread of the data, because RMSE alone just paints a very one-dimensional picture of the performance of a model. Again, how does it perform? What does that spread look? Where do those tails actually rely? What does that distribution of errors resemble? Right? You can perform very well. Talking to kind of getting to Roy's point, you could have measurement data that in a lot of the measurement data you do really well, and in some places you're just terrible, and it could be biased. Like there could be specific morphological scenarios where you're just falling flat in your face, and you need to be able to understand that. And if you just lump that into kind of a single point, you've lost it all. And again, it's this, we're throwing away, and we have to be more nuanced as to when we think about this. I don't know if you guys have any comments on that.
Well, I think my comment is the same as I said before. It's going to be hard to get the tail in the general model. It's really a separate calculation almost to look for things like line of sight propagation. It's a key, right? And within, is there the possibility that this is a line of sight case? That's a big difference than a non-line of sight case without clutter. So anything close to that is a risk area. You need to be able to identify it. It's probably a longer calculation than some of these other models we're talking about, except for ray tracing might, it's a solution potentially. Well, certainly.
Yeah, I think we care about clutter loss. Of course, we care about it. So it's still depend on the scenario. If it's outdoors environment and with the link distance over a few hundred meters, we need to consider clutter. However, the issue is that a clutter model or clutter loss is not very easy to implement. It's unlike the traditional path loss model or the building entrance loss model. Like the linear slope path loss model is very easy to implement, and people understand what's going on over there. And the building entrance loss model is also a distribution. We can just write an equation to model it. However, the clutter loss is way complicated to model. So we may need to think about the 3D building or vegetation data and it's pretty hard to implement. And also, people always thought about the accuracy to rely on it. So maybe that's why a lot of people do not really consider clutter loss.
Actually, I'm going to give you a slight variation of Tinjin, because something that Roy said there, and this has been, you talked about, validating against synthetic data, and, in a way, you're saying we're going to validate this model, see how well it performs on another model that has its own assumptions and simplifications in that. And I'm curious on your comment on that, right? Because you don't have measurement data, and there's value in using that. But for example, in a lot of ray tracing simulations that I see out there, things like vegetative effects aren't even considered because either data availability or the complexity of kind of dealing with those things.
Right. So maybe this is probably where the magic of machine learning comes in, right? So from our experience, is really if you can crowdsource enough sites with diverse enough buildings and landscapes. In our simulation, we really only consider the buildings, the building shapes, and also the building heights. There's for now, the current version we have that is open sourced, there's no terrain profile. It's assuming flat ground. There's no foliage. There's no basically other types of clutters in the environment, right? But what we do is basically we crowdsource many different sites. And although each of those sites contains only a flat ground surface and buildings, you can actually train a model that considers all these different types of building scenarios, and then the model by itself, learns something from this very diverse environment. The other trick that we did was basically we can actually also augment the data, right? For example, you don't have to rely on the output from the ray tracer. You can also add, let's say you look at the link budget equation, you can add your own random variable that represents foliage, clutter, obstacles and terrain. You can actually add this random variable that you can tune its distribution on top of the ray tracing results, right? In other way, you can actually train a model that is not only considering the buildings in that site, using ray tracing, but also you have this other knob to basically generate random perturbance onto the ray tracing results, right? In other way, we think of that random perturbance as a way to represent all these other effects that the building database together with the ray tracer cannot capture. Right? So that was another feature that we introduced to our simulation pipeline. So overall, there's a lot of randomness in the way that you generate data. Underlying it's a ray tracing tool, but every data point that comes out from the ray tracing results, we add a bit of random perturbation on top of that. This can be let's say uniformly distributed between -20 to +20 dB. This could be representing some additional loss in that particular environment, and then we actually randomly generate this data for every site, and we can actually do this multiple times for the same site as well, right? So the way that we generate synthetic data, we incorporate this feature to make sure that the data is diverse enough, not only based on the building information and the ray tracing results, right? You can also orient your antenna in different directions in the same site, and then you basically build a massive database, and this can be trained, in just a few hours. And then that actually gets you a lot of different interesting results. So I know, if you look at all these licensed software, some of those actually have the foliage information, right, the clutters and everything. But you cannot really do that. You cannot really afford that, to be honest, from an academic setting. That's why we went after everything that is publicly available. So for now, we have the publicly available building information from OpenStreetMap. We're looking at the nationwide LiDAR data sets to basically give you scans of different cities. That actually covers the entire US and some of the European countries as well. Right? So if you analyze the LiDAR scan, it also tells you something in addition to the buildings in the environment. Basically, if you have very tall trees, you actually kind of see these clutter points in your LiDAR scan, and maybe that information can be turned into some other types of features in your obstacles or objects in your ray tracing simulation. So that's the next step. So actually, we're looking into adding this LiDAR data set information as well as whatever that's available in the public domain in terms of terrain profile, in terms of foliage, in terms of other types of obstacles and objects that might be available. So we're working on the next generation of this framework, I would say, that allows you to actually run ray tracing very quickly. So going back to Billy's question on the speed of ray tracing, so I can give you some estimate, right? So now we are using NVIDIA's Shauna's ray tracer that is a publicly available open source tool. So if you look at a 512 meter by 512 meter area, if you cut areas into pixels of 4 meter by 4 meter, let's say you look at the resolution, a spatial resolution of 4 meter by 4 meter, you're essentially trying to generate a ray tracing map that is basically 128 by 128 pixels in one image, right? So on a standard computer like MacBook Air with GPUs and those kind of stuff, you can actually generate one ray tracing map in less than 3 seconds, right? So that's kind of the speed you can actually run these ray tracers these days to generate. That's why we are able to actually generate these data sets across a large, diverse landscape. The longest time it takes is actually to crowdsource the building information rather than running the ray tracer, right? And then if you look at how NVIDIA designs the ray tracer, there's actually a lot of rooms to optimize. We keep finding bugs and ways to improve the optimization in NVIDIA's framework, and then we are reporting these solutions and improvements to NVIDIA. The thing is, they assume you have a sphere omnidirectional antenna on the top of the building, and then you can assume I'm gonna emit, let's say, 1 million rays uniformly distributed that are going out from this spherical area, right? So eventually this becomes a memory problem, not really a compute resource problem, because the more rays you want to generate, it takes up more memory in your computing, right? That's why if you look at NVIDIA's GPU with up to 40 gigabytes of memory, you can only generate up to, I think from our experiments, up to 7e⁷. That's like 70 million rays from that single sphere, right? Eventually becomes a memory limited problem rather than a CPU or GPU compute limited problem. And then NVIDIA actually does this very nicely. So that's why from our case study, we keep using NVIDIA compared to we were actually using MATLAB before, which also has the OpenStreetMap building database built in. But MATLAB is actually not unlicensed, right? That's why we moved to the NVIDIA's platform, and then that turns out to work pretty well. You can actually run these very quickly. So one thing that I do want to mention is that we're actually building on top of our DiceBand results. We're actually providing now, hopefully that's going to become available soon, a web interface that anybody can actually just go to an HTTPS URL, and then it basically shows you a Google map, image. You basically click a point in the US territory to specify an area, and then that website directly gives you the ray tracing results in that area. Right? The reason we want to do that is basically a lot of people don't want to go through the entire pipeline to learn how do I port building information from OSM into the ray tracing, to go through this entire pipeline. So basically, we set up a service that runs on our server, and everybody can basically use this service to directly generate ray tracing results without going through the entire pipeline. So from my perspective, that is really a computer software problem rather than a ray tracing problem now, because how do you actually provide this capability to the broader community so everybody can, just by a very quick click, right, get the ray tracing results of a given area, and that shows you the building map information and then the coverage and everything. So we're actually working on providing that capability, and hopefully that will speed up the use of these open source tools by the broader community. Yeah.
Cool.
So just a couple things I just wanted. First of all, I think like your ray tracer outputs a distribution of received power levels, not a single.
It's every single pixel, right? You specify the spatial resolution.
But if you did a ray trace for a particular transmitter and receiver, you would get a distribution, right?
There's actually there are two modes, right? One mode is to say you specify the transmitter receiver pair, and then you run the ray tracer between the transmitter and receiver.
And for that, you get a distribution?
You get the rays. You can specify, up to, I think, 7 bounces or something. Those type of stuff.
It doesn't give you the distribution of received powers?
It gives you the path gain.
Okay.
Not a distribution, just the path gain, and then for each of the path. Yeah.
So there's a lot of uncertainty. So what we do is develop the statistical uncertainty into a distribution of received power. But I wanted to also point out and give a throw out to Miter and Tony, because they developed a similar technique, but instead of coming up with the ray tracing as the engine, they used it to develop an empirical model based on machine learning, and they used ray tracing data to generate the test cases. But there's two things that they tried. One is just to characterize morphology first, which we don't which I assume you don't do, because you assume that it just figures out the morphology you're going to and gives you an output. And then separately they did and I'm talking for you, sorry, but they calculated the full, like you, a distribution for a particular area that would be it would figure out the morphology without informing you of it. It would just adapt to it. But I think so you can get both empirical models using this technique and the full ray tracing site specific.
Interesting. I think there was another question or a couple questions. Okay, go ahead. You get to pick, Jeremy.
So, Richard Bernhardt with WISPA and WinForum. We worked both on CBRS and on 6 gigahertz. And in CBRS, we ended up with one propagation model and some minor clutter analysis. In 6 gigahertz, we applied 4 different models. Do you guys see a blend of models being the answer for looking at things? I know what you said earlier about trying to keep them as consistent models with consistent purposes, but do you see a blend of models working more accurately or trying to do this all wrapped up in one? I represent 750 WISPs that don't do coverage at all. They do point-to-point and point-to-multipoint. And so, you know, where a omnidirectional antenna goes is irrelevant to us. And pine needles are more of an enemy than buildings. So in fact, nowadays with Tirana and other companies using null forming and bounce factor, they're actually using the buildings to their advantage. No one ever uses a pine tree to their advantage. So how do you integrate those two things? How do you get the clutter to be accurate? How do you use it for the use it's supposed to be? And should we be using more than one model at a time or just one?
So before you guys answer this, I do want you stole a comment when they were talking that I was thinking to your point, and so I'm just going to augment something on that. When he's Richard, right? When you were talking about multiple models, I had the thought that came in that because you guys are talking about various different approaches in the modeling technique, and I made me think of hurricane season has started, even though we don't have to worry about that, but you have ensemble models where you have multiple kind of weather models that they all make different assumptions. You touched on this, kind of putting perturbations in, and then you take these different models and integrate them into a final solution. I think that's kind of what you were getting at in a way. I'm just taking an analogy. So let me just augment that portion onto it and get your guys' thoughts on that.
So maybe I can start. So from my experience, because I came from a propagation modeling background. We did a lot of measurements in Manhattan, where, as I mentioned, from weeks of measurements, we get 2 coefficients that we can plug into that model, which is something personally I don't really like. And then and then that's why I went to this other approach where I try to understand how this environment information can help us better shape the model. I think it's not only about site-specific models, but also about device-specific. If you are talking about modeling the RF propagation over the air between the TX antenna and the RX antenna, that is okay. You can have very nice statistical models that characterizes the propagation, right? But whenever there's a receiver involved, it could be a Samsung phone, it could be a Raspberry Pi with LTE modem on it. Everything becomes very different, right? So that's why, from that perspective, we run our measurements using commercial available phones and software-defined radios, different type of platforms, and that's why we don't really, in our study, we don't really try to model the RF propagation. We try to model, for example, how much coverage or how much signal strength the users can actually get or receive when they're, let's say, walking around the campus, working in different types of areas. That's kind of our focus right now. I would say it's not only site-specific, but also device-specific. And then we do these measurements, and eventually, we fit in the machine learning model using a bit of measurement from different types of receiver device. This could be commercial phones, as I mentioned. This could be software-defined radios. And eventually, you just get a prediction output, and then that turns out to be working very well. Right? We not only get smaller RMSE, but also the arrows are actually much more concentrated around the average arrow compared to, for example, the Ericsson model, the 3GPP, urban micro, urban macro, all these standard models, and then it not only outperforms in terms of RMSE, but also outperforms in terms of the span of the arrow and also in terms of the tail performance, right? So with that, I would say I'm pretty happy with that approach because it works on real measurements taken across 3, 4, 5 different types of receiver device. For example, we're taking measurement from the CBRS cell, where we look at the received signal strengths of the reference symbols, the RSRP values, and then we use those as the sparse map from the measurements input to our model, and then we predict RSRP. If you take another value, for example, if you take, let's say, the received signal strength indicator, right? You can also throw that value into your model, and then the model will give you the prediction results in terms of RSSI, right? So I think that's another way I'm looking at the problem. It's not only about the propagation loss over the environment, but also about what the users will actually be receiving on their film. And this may not only be characterized by the propagation loss, but also by, nobody knows like all these other interactions between the actual receiver device with the cells and everything.
So I'm interested on Roy's comment on that, because where you're talking about explicitly taking into consideration the devices, and since Cable Labs partners and works with a bunch of operators on some of this modeling, where either I suspect not all operators have homogeneous types of deployments of different devices or different use cases. When you think about that, do you guys try to stay agnostic to this, or do you think there's a benefit to be, traditionally we think of propagation, we talk basic transmission loss, which means we're thinking about isotropic antennas, and we just kind of put on the blinders, ignore things. But do you think there's benefits to be gained, by being more explicit and blurring that line between traditional propagation and basic transmission loss and the device characteristics that you see kind of actually being fielded, that it needs to be, these models are used to kind of field? Okay,
yeah. Maybe I will talk about Richard's question
first.
Go ahead. For the models at 3 gigahertz and 6 gigahertz, there are a bunch of models available. Its use which model really depend on which environment or which people we're talking about. For example, last year we did a lot of coexistence study at 3GPP. And of course, we need to use 3GPP channel models. And in the next a couple of months, the ITU or Working Party 5D will do a sharing study at 7 or 8 gigahertz. Probably they will not rely on the 3GPP model. And when we talk to the regulation like FCC recommends some model. And sometimes we also recommend our consideration which model to use for FCC. However, it's hard for us to develop our own model, like Cable Labs model, and introduce to the industry, because we need to rely on the common consensus of the group. And also for, like Andy talked about, the chopper scatter model. So it's like mentioned in 1960s developed. So we have never validated that model, and we have no resource or interest to validate that model. So I don't know how accurate is that model, but we need to. That's the only choice for us. We can only use it right now. So for some models that we are capable to validate, we did such kind of job. Like 6 years ago, Mark did a study about a 3.5 gigahertz CBRS band propagation model, and we also did some 6 or 7 gigahertz measurement. So we can only do some for like a terrestrial path loss model or building entry loss model, not as fancy as chopper scatter or clutter model that NTI is doing. And for your question about the device-specific deployment, we recently did some study about a MIMO channel capacity measurement. So that's specific for some fixed wireless access deployment, FWA deployment. In FWA deployment, both base station and the CPE can use some directional antenna or antenna array. And if they enable multiple streams, what is the channel capacity gain compared to a SISO system? Theoretically, for example, if we have a 2x2 MIMO, we have 2 streams. So theoretically, the capacity gain is 2 by Shannon equation, but practically it can never reach 2. And we did some empirical measurement, and that will be a kind of guidance for our members or our operators to do the network planning. So that's something not really available, in the literature.
So just quickly, I'll keep it short. I mean, I think I can't imagine in my career how many of these interference studies, assessments I've done from HF, to optical. But I don't think I've ever seen an example that wasn't unique for each case I've done and driven by the requirements of the equipment, which we just heard. So I'm not, it's not surprising that CBRS and Wi-Fi in 6 gigahertz have differences. Also, add on top of that the fact that this is regulatory. So this is a negotiation in the end when you come up with rules.
I know there's other hands.
There are 3, and at the rate we're going, I think that's going to finish the whole panel.
Well, we'll see. There's a couple
Okay.
other topics I wanted to cover, but we'll see. Maybe
Okay, let's
maybe
do
they'll
rapid
keep-
fire.
Well, let's go to the question. Maybe they'll even tee one up.
All right.
They stumble across it.
My question is for Tingjun. Thank you for talking about your approach using ray tracing. That's quite interesting. What I've understood is that you're doing ray tracing simulations in 500 by 500 meter bins, and then you're using crowdsourced measurements to fine tune that model.
So crowdsourcing the database for simulation and measurements only very small scale. And then that spatial resolution can be tuned, right? You can choose to run ray tracing on larger areas, right? You can do like 1 kilometer by 1 kilometer. That's no problem. You can also, yeah.
Yeah, that's what I was getting at. So 500 meter by 500 meter, you could go to maybe 1 kilometer.
Yeah.
But what about long range prediction? Can you do anything about that?
Yeah, that's a very good point. So I was actually, because we are looking at this EMBRSS airborne radar study as well. So from the ray tracers point of view, I'm not sure how these other ray tracers are performing, are working, but from NVIDIA Astronaut's perspective, you can actually set a transmitter, for example, that is 20 kilometer above the ground, right? Basically emulating, the airborne radar passing across. You can actually even add mobility on that transmitter, and actually that's a new feature NVIDIA just introduced about, I think, a month ago. Right? Basically, they actually make this into a mobility type of emulator as well, right? So I would imagine you can set an area to be very large. We've tried up to 2 kilometer by 2 kilometer, and then that works. That's why I was mentioning before. This eventually becomes a memory and compute power issue, right? If you want to go for larger areas, then inevitably you have to go for lower resolution. Let's say I have to go to larger pixels, let's say 10 meter by 10 meter, or even 50 meter by 50 meter. Right? But there's nothing stopping you from go to a larger area from the software perspective, right? And then that's actually something that we're working on right now to see what is the limit, right? If you wanted to do finer grained ray tracing, I think even on NVIDIA's, I believe on NVIDIA's A100 GPU, like one of the, not the best, but the second best GPU with 40 gig of memory. A single GPU card can support 512 meter by 512 meter area with a spatial resolution of 1 meter by 1 meter, right? That is able to run on a 40 gig of memory NVIDIA GPU. But now if you want to go for 1024 meter by 1024 meter while keeping the spatial resolution to be 1 meter by 1 meter per pixel, then you run into these memory issues, those kind of stuff, right? So there's going to be a trade-off of, in terms of the area they want to cover versus the spatial resolution that you want to achieve using such ray tracer. But there's nothing fundamentally not supported by the software. It's more of a compute resources limited case for now. Yeah.
Well, let's take the other question.
Yes. By the way, this ray tracing area is very exciting, very new. You had said something, and I may have missed it in the earlier part of your discussion, Professor. You could handle up to about 7 bounces. Did I understand?
For now, we set our simulation to be, if I remember correctly, we set about 70 million rays to be emitted from the transmitter, and then we set up to, we enable like reflection, diffraction, like pretty much everything, and then for reflection, I think we set up to 7 bounces, right?
Okay, so that was going to be my next question. You handle diffractive interaction as well as reflective.
Yes, yes.
And do you handle vertical as well as horizontal edge diffractive?
Yeah, that's a good question. I think that's by default. We basically use the default setting in Shana. What we care more is actually the interaction between the polarization, right? You can even set your antenna to be horizontally polarized versus vertically polarized, and you can also enable both H and V polarization at the same time, right? So whether it's vertical diffraction or horizontal diffraction, if you look at the perspective of the polarization, they become the same thing, right? Essentially. So that's why we tune the setting. We try different polarizations and try to estimate how the polarization would affect the ray tracing results, and then that's what we've been working on so far. But I can look more into, how Shana is actually supporting diffraction, but we just use whatever Shana's supporting for now.
One of the things we jump in on that we're because this might give me a ramp to one of the topics I want to talk about is, whether we're using ray tracing or whether we're using empirical based models, we're having, so Tien-Tsin, you mentioned the ray tracing, they're not dealing with trees or terrain. We always have these assumptions that we use to frame problems. And even within that ray tracer yourself, you talked about, I'm sure there's other implicit assumptions. If you're talking about an airborne platform, there's some sort of assumption on the atmospheric profile and the effects of what that refractivity is going to do to ray paths, whether they're doing optical ray tracing or they're taking into account refractive effects. And I guess I'd ask you, I'll start with either Roy or Ted, how do we deal with these assumptions? We talked, earlier in this conference, we talked about like these implicit assumptions that can cause problems down the road because we might know they're there, but then you give a model to a regulator and they're being applied and they don't understand what those assumptions are and they're misapplied, or the assumptions are just implicit and we're not even truly aware of what's going on, especially when we're using other tools. So how do we deal with assumptions? Assumptions are really valuable to make problems tractable, but hidden and implicit assumptions can cause real problems down the road for misapplied kind of solutions.
So you mentioned specifically atmospheric effects?
Yeah, so I use that as an example. Tien-Tsin mentioned that in this ray tracer, you can have a 20-kilometer terminal.
Yeah.
There's clearly some sort of assumption of what that atmosphere looks like. Whether they're just doing an optical ray trace like you might do on a terrestrial, you don't have to really worry about those things. But now you have these assumptions that have to be baked in.
Remember that your ray tracer is really looking at endpoint clutter more than anything. I mean, you can talk about long paths, but once the rays get above the clutter, if you're talking about a very long path, then the actual rays that actually reach a receiver are going to be really reduced, because what's the probability that a particular angle will actually hit something really far away? It's only going to be a small delay spread. Instead of the big delay spread, you have endpoint clutter nearby. So I think in terms of that kind of a distance, you're not talking about atmospherics. So you can separate out those kind of models. For the longer part of the path, you can include some of those atmospheric effects with other models, like I guess P528 or something. But I guess there was a case, and there are always exceptions, where you talked about troposcatter, which could be blocked by clutter and affect the result there. Again, you probably are looking at, for something like that, which I think is usually, well, over the horizon it's not, but in terms of overall interference is generally a secondary effect, such as also ducting is sort of a secondary thing because it's very high. Duct is just as likely to block you as it is to cause additional interference, and probabilities are low, even much lower than these corner cases where you have line of sight type things. So you can mostly separate out these models and apply them separately, I think.
Yeah, but I guess what I'm asking is, the assumptions that are baked into the creation of the model. How do we make those more explicit to the user and understand what's there and what's kind of what's that model built on? It's built on some sort of foundation. The problem was, you had requirements.
Documentation.
Documentation would be really nice, and I know how much everybody in this room likes writing it.
Well, it's your job.
Really, I mean, what? Who even brought? I think it was even Claire during the fireside chat said SG3 has a database and it's used to generate models. And there's a comment from someone else about measurement bias in there, and those things aren't present in the models, right? There's assumptions built into what 21A has an empirical model in there, and do any of you, I mean, Roy, right? Could you, if I put you on the spot, know what those assumptions were and any biases in that, right? Because there's always something.
Yeah, so for any channel model, there are a lot of assumptions, like simple assumption like the frequency range or the distance or the morphology. If we dive in, so there might be dozens of assumptions. And any channel model is a trade-off between the accuracy and the simplicity. And sometimes we need to simplify the assumptions to be able to modeling environment. Yes, and sometimes we need to add some more assumptions to make that to make the model more accurate. For example, Billy mentioned multiple times yesterday and today, the clutter model could be between point to point or the point to area. That is a basic assumption we need to define at the beginning before doing any measurement or modeling. And there are a couple of other parameters we need to think, other assumptions we need to think before the modeling. For example, if we think about metrology, to measure clutter model, we can use like a CW tone, multiple CW tones. That's a very efficient way to measure loss. But most of the channel sounders nowadays are wideband, and it can resolve multipass component. And about 10 years ago, a lot of channel sounders are put on a virtual circular wave on a rotator so that with a fancy post-processing algorithm, we can resolve the angle of arrival or angle of departure. That's very fancy, but that's very time-consuming to do the measurement and very time-consuming to process the data to generate the model. We need to tailor or trim down the assumptions for our measurement use case. For example, for the clutter model, for the clutter loss modeling, the bandwidth, the measurement bandwidth, and the capability of angle of arrival measurement, angular resolution capability, that's probably a secondary priority. So yeah, that's some of my consideration about how to simplify the assumption. And on the other hand, sometimes we need to add more assumptions to make the model more complicated. We compared the 2108 model and with the NTIA model today and yesterday. Think about a 2108 model. So there's no clutter data, or there's no building height or vegetation data in the 2108 because that was developed a long time ago, and that clutter data was not available. But nowadays, with the involvement of technology, the clutter data is kind of widely available. At least for in the US, it's kind of available with some not a very accurate resolution. It's available. Nowadays we can leverage those new resources into our channel modeling. Even it adds some complexity into the clutter model, but I believe that's a better way to model clutter loss compared to the traditional urban, suburban, or open space method.
Thank you. If I may go back to using ray tracing generated data as synthetic data for machine learning training. And I understand the machine learning model after that is recalibrated with sparse measurement data. So ray tracing data based on OpenStreetMap, just the building frames. There's no building materials there. So there's no information on the structure of the facades or anything like that. Also, there's no information on vegetation. How do you overcome those challenges, and how is that resulting in some difficulties at the end? Okay.
Yeah,
thank you.
yeah. So yeah, that's also the question we had when we started to use OpenStreetMap. Basically, you know, the default building, the materials can be just, you know, concrete, you know, walls. This could be brick, right? Basically, we use whatever that is the default option that OpenStreetMap provides, and then just magically it just worked. I mean, I think, you know, going back to Billy's question, I think of these less of a modeling problem. I think of the problem, you know, from the systems perspective in terms of building a tool or building a framework that gives you the prediction results that you would like to see, right? So this is definitely going to be site specific. For example, if you want to understand, you know, if I want to deploy a cell on the top of this building at 3.55 gigahertz, how does it cover, let's say, 1 kilometer square of area around this area, right? So I can build a tool that provides you the prediction results about that, right? So there's less modeling involved actually in building this tool, right? So that I think that's my perspective of thinking about this whole, you know, propagation modeling thing. I don't really think of it as a challenge to find a better model that statistically matches, you know, the measurement results across diverse areas. I think of it more of as building, you know, a better tool that allows you to input as much information as you can for this given area. Let's say for this given user device, for this given, you know, cell deployment, that tool or that framework will tell you this is the coverage map. How does it look like when you actually put that cell over there? Right? So from my perspective, I think of it less of as a modeling problem, but more of a building a tool or a framework that gets you the results that you want to see. Right? So that's my perspective of why we're looking at this ray tracing based method. There's really, you know, little to do with modeling here, but that basically does the job very, very nicely. And also, I think it sounds like I'm advertising for NVIDIA today, but NVIDIA actually has another tool now. I think it was just released maybe last month. They actually incorporate the clutter models into their MIMO link layer framework, right? So basically now you can actually go to this NVIDIA framework, which is completely open sourced. You ignore the ray tracing part, and then basically set up the transmitter, the receiver. You specify I run an OFDM PHY, and then I tell the model between the transmitter to be and the receiver to be based on this clutter model, right? Actually, NVIDIA does that already. So they have some, you know, standard building clutter models and all these 3GPP standard models they are actually already built in. So even if you want to investigate, you know, the performance of these models with measurement data, you can completely ignore the ray tracing part and then rely on these models to, you know, to get the results, right? So that's another capability that these, you know, I'm all for open source today. So that's why I keep mentioning, you know, these frameworks. But I think that's going to be a very helpful tool. You know, one is how do you actually create better models? But from my perspective, I think of it as more of a, you know, a way to build better frameworks and tools, which allows people to actually get the desired output from the tool. Yeah.
So just to add to that really quickly, this is a reason why you want to keep the data that you're training on, especially if it's measurement data, because at some point you're going to get the building material for each building individually, and the training will be better for that.
All right, one more, Billy.
Yeah, go ahead.
Okay.
It's a simple question, actually. I've heard a lot about the ray tracing models, and if you take a particular geographic area outside, not internal penetration or anything, how does ray tracing compare to, let's say, an ITM in the probability distribution function case? So, or some other model that we have in the literature already. Just wanted to see a comparison.
Yeah, so we actually have looked at these across measurements, right, on our campus, and also now we're actually looking at measurements that, together with Monisha's team, which are taken from other areas. So it's really site specific, right? So in some areas, you know, some of the, even like, for example, we compare Erickson's model, you know, the 3GPP urban macro model, the urban micro model, and then we have, you know, the standard, you know, ray tracing model and some other baseline machine learning models. So overall, this model performs really differently, right? So in some scenarios, you know, the ITM model performs better than Erickson. In some other scenarios, Erickson model performs worse than, you know, better than, you know, ITM model, right? This the ITU model. So that really depends. But, you know, from our experiences, our method consistently outperforms all these other models in all scenarios, right? So let's say you compare our method with 5 other baselines, which can be, let's say, 3 statistical model based, plus 1 analytical model plus 1 machine learning baseline model. Across different areas, these other 5 models, they behave differently, right? Sometimes model A is the best, sometimes model D is the best, right? But across the areas, our method is actually the best across all the models, and then it's consistently outperforms the second best model by 2 to 3 dB in terms of RMSE, right? So I think that's I'm not really advocating for machine learning, but I think this is really the place where machine learning actually works to some extent, although we don't really know why it's working like that. For my other research problems, research areas, I try to avoid machine learning as much as possible. But for these particular areas, in terms of reconstructing the coverage map and then the spectrum coverage, those type of things, machine learning seems to be working pretty nicely. That's what I can tell from our study.
So just quickly, I think Billy showed it, and then SSTD, they showed it. If you're talking about an area that's, suburban, where there's not heavy multipath, the single direct path, which is modeled by ITM, is pretty accurate. It's when you get into this dense urban where you have lots of multipath that even you showed, I think, that the tail gets, you're off on the tail is way off. So that's where you start needing to use the 3D ray tracer. And which models you use at this point come down to, I guess, how much time you have and how much speed you need, and if you have an NVIDIA chip, I guess.
Yeah. So I want to close. I want each of you guys to answer this, but I want to close to kind of bring this back to the topic of the conference. So we talked about a bunch of different modeling approaches and technologies that we're using. I would posit that just because, and you've seen this in various fields of technology, so I'm not really going on a very, not going very far on a limb when I say this, but just because you have, I'll pick on you, Tien-Tsin, for a minute. Just because you have, you may have the best simulation and ray tracing, and it on the metrics does everything, that actually in and of itself does not ensure consensus or standardization, right? Those are 2 different things. They're related, and there's interplay between them. But there's both a pushing technologically forward, but then also bringing people to that point. So I'd like each of you guys to comment on that aspect of it, right? If I brought Claire back up here and she talked, I'm sure she would acknowledge some of the things where, just even across any of the ITU models, there's deficiencies, there's ways you perhaps could do things better, but you also have to get people to agree that that's how you should solve problems. And that's not always a technical challenge, but I think it's always important that when we're going about modeling what we're trying to do, we need to bring the people with us, whether it's making data available, whether it's documenting what's going on. So I'd like each of you to kind of, as our final thing here, we just have a few minutes left, say some comments on that, is to kind of bring to the consensus of model, even acknowledge that may not be state of the art, in air quotes, whatever that means, or number 1 in some sort of rankings, because that's an important thing, because without that, we're just all left doing science experiments.
So I think the most important thing to me, and I think there was a question that's on the last panel, is the most important thing is the model works, and you demonstrate it through some kind of documentation that it works for these cases, and it's trustable to those cases at least. That's the most important thing. Why it works, who cares? If it's working, it's working. Because machine learning, you're never going to follow the hierarchy of decisions that go in there. In addition to that, well, I'll leave it. I'll stop there because we're running late.
Roy?
Yeah, I think we're talking about the trustworthiness or the documentation of the models. Well-documented model is very critical. For example, like I mentioned at the beginning, Winner 2 model mentioned it's an empirical database, and they detailed the frequency range, the distance, and many other parameters. So when we use the model, we know which area we are confident and which area we are not confident in, and we need additional validation. However, when we use the 3GPP model works up to 100 gigahertz, and it never mentioned what they rely on to build the model. So when we use the model, we always have some question mark in our heart. So to confidently use that model. Yeah, I think that's my consideration.
The extrapolation of models is always fraught with risk. Tien-Tsin.
Yeah. So I think that what Billy was mentioning was a very good point. So when we were working on ray tracing, we also think about how does this relate to all the models. Whenever we talk about model, we think about there's a standard behind the model, right? There's a group of people working on pulling out the model, make sure it's statistically correct, and then empirically verified. I think if there's a way that we can somehow combine statistical models into the ray tracing framework, that would be a huge plus. But on the other hand, when you get massive simulation data, then basically the effectiveness of these statistical models get amortized as you have larger and larger areas and then different types of measurement data, right? So that's why I keep mentioning I'm not looking at building a better model because that's very challenging, but also very important. I'm more looking at the perspective of building a framework that does the job. The job here could be estimating the coverage of a CBRS cell in this given area. Right? Could be estimating, if the user is moving around, how does the signal strength change as the user move around? I think of these as a framework that will give you, as good of a result as possible when you are given a task, right, to accomplish. And maybe one final conclusion I want to make here is that we didn't really touch much upon interference, right? I think one thing that we're looking at today is how do we actually evaluate the interference in different areas, right? So if we're looking at how statistical models can be applied to model interference, which is highly depending on the spatial distribution of where the energy comes in, not only from the primary cell, but also from the secondary cell and some other potential interference, it becomes very challenging to think about how do you model interference using statistical models, right? On the other hand, if you were using ray tracing models, at least you have the knowledge of where the signals come from. And then we're thinking maybe that is a better way in terms of modeling not only the signal coverage map from the primary cell, but also estimating the interference map. That's the interplay between the primary cell and whatever interference sources that may be out there from other parts of the area. I think that's the final conclusion I want to make. I think the next step is really to not only look at the coverage, but also look at interference. That's,
So I'll just say as a closing remark and also tee up for tomorrow, so folks come back. The one common thread, we talked about a bunch of different methods here and different thoughts on that. The one very definitive common thread that traced through this whole conversation we've had for the past 90 minutes, and all the panelists brought it up multiple times, is the importance of measurement data. So whether it's crowdsourced or whether it's going out in the field and collecting with the measurement data, whether wideband or CW, there's a lot of even synthetic data. There's throughout this whole thing was laced as an undercurrent of using the measurements both to get at the type of problem we're doing and to validate what's going on. And I bring that up because tomorrow Adrian will have a panel up here and they will be talking specifically about measurement data and how we kind of acquire and how we think kind of more open on that topic. So I'll leave it at that as my final word as an intro for tomorrow's panel, because I think it segues really kind of, like I said, what underpinned a lot of what was discussed here. And Jeremy, I'll turn it to you to bring us home. Let's have a round of applause for the panelists.
And for Billy Grossman. Thank you, Billy. All right. I wasn't at the mic yet, so that would have been awkward. Wait for that one clap. All right. It is 5:30 here Mountain Time and 7:30 for folks who are still online with us Eastern Time. Let's go have dinner wherever you're going to eat. I'm hungry, so I'm going to go eat some food. Thank you you survived the longest day of ISART. Tomorrow is going to be 30 minutes shorter. We will reconvene here in the plenary room at 9 a.m. and to hear from Billy again. Thank you so much. Have a great evening.